The datapath controller machine is a foundation for the design of CPUs and many other types of digital systems. One or several data values are read from registers in the datapath. Operations are performed by the datapath's ALU. The result is written back to a register. The distinction between data and control is very useful in thinking about sequential machines, but this distinction is a little arbitrary. Here, an AND gate generates a data signal. We feed that signal into the control input of a multiplexer. Whether we view the signal as data or control depends in part on which end of the wire we're looking at. This datapath controller system is divided into two components. A datapath provides registers and data operations. A controller manages the operation of the datapath to perform the desired functions. This division of labor uses divide and conquer to improve the design. Controller FSMs use less structured logic. On the other hand, datapaths often perform regular operations like addition that call for different design techniques. This datapath has three main components. The arithmetic logic unit, or ALU, performs arithmetic and logical operations, shift, plus, and so on. The register file is a set of registers that holds values. The register file is organized as several words. A register file may allow several words to be read at the same time. It may also allow a register to be written. A temporary register captures the ALU result so it can be saved back later to the register file. We start an operation by selecting two words to read from the register file. The words flow into the ALU. An opcode determines what operation is performed by the ALU. The ALU's result is saved in a temporary register. On the next clock cycle, that value is written back into the destination register in the register file. We can design an ALU as a set of combinational logic operators and a multiplexer to select the right result. This ALU performs plus, and, or, not, logical shift left, and logical shift right. Other ALUs can be designed with more or fewer operations. An opcode feeds a multiplexer to choose which of the functions is used as the result. Some ALUs include status logic for the result, such as 0, negative, or carryout. Here's the ALU performing an add on two operands. Here's the ALU performing a negation on one operand. Let's spend a minute reviewing computer arithmetic. Programs make use of both unsigned and signed arithmetic. Unsigned can be used for pointer arithmetic, for example. Signed arithmetic is common for applications. Our ALU can use the same logic to perform both signed and unsigned operations. You can see that the unsigned and 2's complement ranges here for a 3-bit value are the same size but cover different parts of the number line. We can interpret the binary number in either way. Here's an 8-bit number. As an unsigned number, its decimal equivalent is 177. As a 2's complement number, its decimal value is -79. To perform the negation of a 2's complement number, we first form the 1's complement, flipping every bit in the number. We then add 1 to that result, creating the 2's complement. We can test a 2's complement number for negativity by looking at the most significant bit. We can test a value for 0 by NORing all of the bits together. A shift can be performed as a combinational operation using wires. In this case, we've shifted left by 1 bit. A rotate would move bits shifted out of the most significant positions into the least significant, or in the other direction from the least to the most significant. The register file uses a specialized circuit based on static RAM to provide both speed and compactness. We can't read all of the values in the register file at the same time. We use ports for parallel access to more than one word. For example, we can provide 2 read ports that can be operated in parallel. We can also use a write port to write a value back to the register file. We add the temporary register to the data path to avoid combinational cycles if we tried to write directly from the ALU back into the register file. The controller is a finite state machine. It takes inputs from the data path and from the outside world. It generates control signals for the data path as well as external outputs. The state transition graph or table of the controller determines what the data path controller system will do. Separating data path and controller helps because data paths use regular and specialized circuits, while controllers can take advantage of logic and physical optimizations during synthesis. We can change what the machine does by changing the controller FSM, the operations and registers on the data path, or both. Thanks for watching.